In today's lesson, we're going to continue looking at hypothesis testing when we have two samples of data. But unlike in the last situations where we were looking at this, where we were assuming that we had independent samples of data, in today's lesson, what we're going to be looking at is what if we can actually pair off the data? What if they're not independent of one another? And so with the lesson today, what we want to do is construct hypothesis testing confidence intervals for two sample data if the data are paired, right? So it's a very specific kind of non-independence, and we'll look at exactly what that means in just a few moments here. So a motivating example, you can think about car tires, right? So one of the things that you might hear people talk about is that different tires will improve the fuel efficiency of a vehicle, right? So if you think about how you might try to test this, one of the things that you could do is you could get the two different sets of tires, your regular tires and then the fuel efficient tires, and you could install each on a set of vehicles and then drive the vehicles with each of them and sort of measure the fuel efficiency there, right? The data that you're getting out of this is going to have, an average fuel efficiency for the first tires, average fuel efficiency for the second tires. But if you drive the same cars for each of those groups, which you probably should, because of course different cars are going to have different fuel efficiencies, even different cars of the same model are going to have slightly different fuel efficiencies, then for every observation you have in the group of tire 1, there's going to be a corresponding observation in the group from tire 2. And so the data are naturally paired to one another. And because those data are naturally paired from one another, it seems like we should be able to make use of that structure in order to improve the procedures that we're looking at. So sometimes there's going to be this natural pairing of data between two different samples, right? So if we give two different treatments to the same individual, if you do some sort of before and after testing, right? So if you test something beforehand, you do some intervention, you test something after the fact. If you have studies of twins, this is quite common to do. The twins are going to be sort of naturally paired, where you might think about the twins as having, similar genetic components, but different experiences. In that case, we can sort of think about how the data that we have changes. So we'll have x1 through xn with mean mu1 and variance sigma 1. Then we'll have y1 through yn, right? Of course, there's going to be a one-to-one correspondence. So in this case, the two samples will be exactly the same size. We'll take the mean of y to be mu2 and the variance of y to be sigma 2 squared. Now, any of the corresponding x and y are not going to be independent of one another, right? And this is going to be true because, you're testing the same unit, or you're assuming that there's some sort of natural pairing there that causes a dependence. We'll still assume that each of them are independent of one another, but not the corresponding x and y observations. And so the question is, how do we do hypothesis testing or build confidence intervals when this is the setup that we have? Now, because the data are naturally paired, what we could do instead of thinking about grouping everything together in their x and their y group is we could actually just consider the differences, right? So if you want to know what the difference between x and y is, and there's a natural pairing, well then for each observation, you could take the difference between, x1 minus y1 or x2 minus y2. And doing this is going to give us a set of differences that we can look at where those differences make sense to compare because each of the observations was directly paired with one another. So what we do is we define di to be the difference between xi and yi. So it's the ith difference, right? x1 minus y1, x2 minus y2, and so on. And then what we do is we treat those d observations, or the observations of d, as though they were observations from a single population, okay? And this seems to make a little bit of sense because, again, we sort of had whatever process that we were testing naturally gives us out a difference measurement. And if we just thought about measuring the difference directly, well, then we just have a univariate measurement again, right? And once we have a univariate measurement, we've already seen how to do hypothesis tests. We've already seen how to form confidence intervals, right? It's going to depend on the distribution of these differences, but we could treat this no different from any other single sample. So if x and y are both normally distributed, then d is going to be normally distributed as well. The variances of them are going to be given by the variance of x plus the variance of y minus 2 times the covariance. And the covariance is not actually a quantity that we have seen before up until now. And so I'll just briefly take an aside to talk about it. Right? So in this case, sigma 1, 2 squared, this is called the covariance. And it's specifically the covariance of x and y. Right? And what we would do is we'd actually write this down as sort of cov here, covariance of x and y. And if we're thinking about this in the population, then what this is going to be is this is going to be defined to be the expected value of, and then we're going to take x minus mu1. We're going to multiply that by y minus mu2. Okay. And so you get this term, which is x being centered by its mean. You get this term, which is y being centered by its mean, right? And then you take the expected value of that. Now, doing this actual expectation calculation is going to sort of depend on the actual distributions that we're looking at under the surface here. But just note that this is the covariance, and we sort of won't dwell too much more on this. Now, the mean difference, so if we're taking d bar, then this is going to have variance equal to its variance, which is sigma 1 squared plus sigma 2 squared minus 2 times the covariance, scaled by the sample size, which in this case is n. And then we can treat this as any standard one population sample, right? We have our variance. We have the mean difference is going to depend on the hypothesis that we're testing, say. And so now we can just do a one sample hypothesis test or confidence interval. If the variances are known and normality is assumed, we can use a standard normal distribution. If the variances are unknown, but normality is assumed, the sample size is large, we can use a normal approximation. If the variances are unknown, normality is assumed, the sample size is small, we use the t-distribution. Right? So those are sort of the standard cases that we're used to thinking about. And so then it proceeds exactly as you would expect, right? And then it's no different than what we've seen before. Now, the caution that I'll put out here is that paired data should be used with caution, because these results are going to generally be less conservative, right? If you think about the variance that we were looking at when we just did two sample data, right? We got a variance of sigma 1 squared plus sigma 2 squared divided by the sample size, right? In this case, we get to take off the covariance. And generally speaking, the covariance is going to be a positive value. And because of that, we're going to end up with a smaller overall variance here. We're actually sort of underestimating the variance in a way, right? And so when you do this paired analysis here, you're going to end up with a smaller variance. You're going to end up being less conservative. And so there's a lot of times where paired data makes sense, right? Where we're talking about the examples where you're actually testing the same unit multiple times. But if you can't directly pair the data, you really should not be using a paired test, okay? And so you'll see this sort of be one of the cases where researchers trying to get a specific result might end up using this in an inappropriate way. And so I would just avoid or issue you caution to avoid doing that. So in summary, if the data are paired, we can consider their differences as though it was a direct observation. Results in a single sample, which we can then use any of the procedures that we've previously seen to apply to that. The variance of the sample is going to depend both on the individual variances as well as the covariance between the two samples. We're not going to be too concerned with what the covariance actually is, but just remember how it was defined and note that it's normally going to be a positive value, at least in these situations. In the next lesson, we're going to be looking at paired proportion tests, and then that will mark the end of hypothesis testing before we enter into the last section of the course. So I hope to see you all in those coming lessons.